Hello, I'm Colin Phillips.
And I'm Colin Jung. There are many and varied differential equations that arise from nature and science. Many of the important differential equations in nature involve not only a first derivative, but a second derivative, or even higher derivatives. If the highest derivative is a second derivative, then they are called second-order differential equations. Here, we will consider a very special class of second-order differential equations, which takes the following form.
This is called a second-order linear, homogeneous, constant coefficient differential equation. In this module, we will explain what each of these terms mean. We will also learn how to solve this differential equation, that is, find the general solution for the first of three different cases. We will then show how to evaluate the arbitrary constants in the general solution using boundary conditions to give the particular solution. We will also explain when the different cases apply and how they relate to each other. We will explore the other different cases in a later module.
Slide 1, Introduction. To start with, we introduce some ideas with a specific example of a second-order differential equation, where the second derivative of some unknown function p minus 5 times the derivative of p plus 6 times p is equal to 0.
We can think of this differential equation as posing a question. The differential equation is asking us to find a function p, which is a function of t, such that if you differentiate the function twice, then subtract 5 times the derivative of the function plus 6 times the function, you get 0 for all values of t.
Can you think from the top of your head a function that answers this question? It's quite difficult, isn't it? In fact, some people spend their lives solving very specialized differential equations.
It turns out that p of t is equal to e to the 2t satisfies the differential equation. Now we can check this by simply substituting e to the 2t into the dE and verifying that it satisfies the differential equation.
To do this, we differentiate e to the 2t to give dp dt is equal to 2e to the 2t, using the chain rule. And differentiating again gives d2p dt squared is equal to 4e to the 2t.
Now to show that e to the 2t satisfies the dE, we substitute it and its first and second derivative into the left-hand side of the differential equation.
Thus, the left-hand side, which is the second derivative minus 5 times the first derivative plus 6 times the function, becomes 4e to the 2t minus 5 times the first derivative, 2e to the 2t plus 6 times e to the 2t, which simplifies to 4e to the 2t minus 10e to the 2t plus 6e to the 2t, which adds up to 0, which is precisely the right-hand side. Because when we substitute e to the 2t into the differential equation, both sides are equal, this means that e to the 2t is a solution of the differential equation. Sometimes we say that e to the 2t satisfies the differential equation.
Importantly, when we find the various derivatives of e to the 2t, then we always get a multiple of e to the 2t. This means that when we substitute the function or any of its derivatives into the dE, we get a constant times e to the 2t every time we substitute. Here, this combination of e to the 2t adds up to 0, which is exactly what we wanted. Importantly, we note that the 2 in the power of e to the 2t is very special, and this doesn't work for just any power. That is, The power 2 means that the special combination of constants times e to the 2t adds up to 0. We will see later how we come to this special number 2 in this dE.
Slide 2, Introduction continued. In this module, we will learn how to solve a very specialized class of second-order differential equations.
We will learn how to solve the differential equation a d2p dt squared plus b dp dt plus cp is equal to 0, where importantly all of the coefficients of p and its derivatives are real constants. That is, a, b and c are real constants.
This dE is said to be second order, linear, homogeneous with constant coefficients. We will now explain what each of these terms mean. Slide 3, Terminology, second order. A differential equation is second order if the highest derivative is second order. That is, if the highest derivative is a second derivative. Here, we will give examples of second order differential equations and compare them with dEs that are not second order.
So this dE is second order because the highest derivative is d2p dt squared.
Whereas this dE is not second order because the highest derivative is just dp dt.
This dE is second order because the highest derivative is given by x double dashed, or x double prime, which is a second derivative.
Whereas this dE is not second order because the highest derivative x dash is a first derivative.
This dE is second order because of the second derivative d2p dt squared.
Whereas even though this dE has a second derivative, the highest derivative is d3p dt cubed, which is a third derivative, which means it is actually a third order differential equation.
This dE has its highest derivative as p double dashed, so it is second order. Note, we do not have to have the first derivative in the dE for it to be second order. In fact, we do not even have to have the function p.
On the other hand, the highest derivative here is p triple dash, so it is once again third order.
Note that it doesn't matter where the highest derivative occurs, or even if the other derivatives are in the dE or not. It is nevertheless still second order. For each of the differential equations on the left in black, the highest derivative is a second derivative, unlike each of the equations on the right. The highest derivative alone, wherever it is located in the equation, determines the order of the dE.
Slide 4, Terminology, linear. A condition for a differential equation to be linear is that there are no products of the dependent variable or its derivatives. Here, we will give examples of second-order linear differential equations and compare them with dEs that are not linear, often called non-linear dEs.
This differential equation is linear because there are no products of p or its derivatives. All the relevant terms p, dp dt, or d2p dt squared never multiply each other or themselves.
However, this dE is not linear because the term p squared is the product of the dependent variable p by itself, which is not allowed.
This differential equation is linear because there are no products of x or its derivatives.
whereas this dE has a product of the first derivative x dash with x, and so it is not linear.
This dE is linear because even though there is a product of 2t with p dashed, there are nevertheless no products of p or its derivatives.
Whereas this dE is not linear because there is a product of p with its second derivative.
Finally, this dE is linear because even though there's a product of 5t squared with dp dt, there are nevertheless no products of p or its derivative.
Whereas this dE is not linear because there is a product of p dash with itself, and also p dash with p double dash.
Again, the condition for a differential equation to be linear is that there are no products of the dependent variable, like p or x above, or its derivatives in any combination.
Slide 5, terminology. Homogeneous. A linear differential equation is called homogeneous if every term contains either the dependent variable or one of its derivatives, apart of course from 0 on its own. Here we will give examples of second-order linear homogeneous differential equations and compare them with dEs that are not homogeneous, sometimes called inhomogeneous.
This dE is homogeneous because every term involves the dependent variable p or one of its derivatives, dp dt or d2p dt squared here, apart from 0 on its own on the right-hand side, which is allowed.
On the other hand, this equation has a 3 on its own on the right-hand side, which means it is inhomogeneous.
This dE is homogeneous because every term involves the dependent variable x or one of its derivatives x dashed or x double dashed.
Whereas this equation has a 5t on its own. Now, even though the term involves the variable t is an independent variable. Because the term doesn't involve the dependent variable x, the equation is inhomogeneous.
This dE is homogeneous because every non-zero term involves the dependent variable p or its second derivative d2p dt squared.
Whereas this equation has a t on its own, and so it is inhomogeneous.
Finally, this dE is homogeneous because every term involves either p, p dashed or p double dashed.
Whereas this equation has a constant term e cubed, which clearly does not involve p, and so it is inhomogeneous.
Now recall that the condition for a differential equation to be linear is that there are no products of the dependent variable or its derivatives. This may seem like an unusual condition, but there is an important reason why we consider linear differential equations. If the dE is linear and also homogeneous, then the dE has a very important property.
If we add a solution to a linear homogeneous dE to a second solution, then this sum turns out to be yet another solution. This way, we can construct a brand new solution from two known solutions. To take this idea even further, if we add a multiple of any solution to a multiple of any other solution, then this again produces a brand new solution.
That is, any constant times a first solution plus any other constant times a second solution is also a solution. And because there are an infinite number of ways of taking the constants a and b, we can construct an infinite number of new solutions from just two known independent solutions. This is a very powerful concept for solving these type of differential equations, and we rely on this important property to solve the DEs in this module.
The combination of a constant times a solution plus another constant times another independent solution is called a linear combination of solutions. Indeed, this property of a linear combination of solutions also being a solution to the DE is where the name linear comes from in the first place.
So in summary, if a DE is linear and is also homogeneous, we can add up any linear combination of solutions, and this will also be a solution. We will use this very special property to construct the most general solutions to our DE.
Slide 6. Terminology. Constant coefficients. A second-order linear homogeneous DE is said to have constant coefficients if the dependent variable and its derivatives are only ever multiplied by constants. Let's say the dependent variable is p, like in most of our examples. Then a constant coefficient DE will only have a constant times p or any of its derivatives. Here, we will give examples of second-order linear homogeneous constant coefficient DEs and compare them with DEs that do not have constant coefficients.
This is a constant coefficient DE because the coefficient of each term is a constant.
Whereas in this equation, the coefficient of the derivative dp dt is t, which is not a constant.
This is a constant coefficient DE because the coefficient of each term is ultimately just a number.
Whereas in this equation, the coefficient of x is t.
This is a constant coefficient DE because the coefficient of each term is again a constant. Even though pi is an irrational number and cannot be expressed in a finite number of decimals, and 1 million is large, these are all just constants.
On the other hand, in this equation, the coefficient of both p' and p are functions of t.
Finally, this is a constant coefficient DE because the coefficient of each term is again just a number.
Whereas in this equation, t cos t is not a constant.
To summarize, a differential equation that is second order, linear, homogeneous, and constant coefficient is an equation involving, at most, second derivatives, where there are no products of p or any of its derivatives, and every non-zero term includes p, dp dt, or d2p dt squared, and each of these are only multiplied by constants.
Thus, such a DE will only have a constant times p, or a constant times dp dt, or a constant times d2p dt squared.
Even though you may only be asked to solve differential equations like the ones in this module, it's important to understand that there are many other types of DEs, and that here we're going to solve just one very special class of these.
Slide 7. Overview of cases. In this set of modules, we will learn how to construct the general solution to our second-order linear homogeneous constant coefficient differential equation.
The general solution of this dE can take different forms depending on the real coefficients a, b and c. In this slide we will outline how to find the general solution to this dE for 3 different cases. To decide on which case to use, we will use a special combination of the constants a, b and c, called the discriminant. The discriminant is often labelled with the capital Greek letter delta and is equal to b squared minus 4ac.
You may recognize the combination b squared minus 4ac as part of the quadratic formula, which is often used to solve quadratic equations. Indeed, during the process of solving this dE, it turns out that we will need to solve a very special quadratic equation called the characteristic equation. Now, depending on whether the discriminant is positive, 0, or negative, we get our 3 different cases.
If the discriminant is positive, this corresponds to case 1, and the general solution takes the form of the sum of 2 different exponential functions. This is sometimes referred to as the real exponential form.
If the discriminant is 0, this corresponds to case 2. The general solution for case 2 looks very similar to case 1, but there are some important differences. For instance, there is an extra t in front of the exponentials. The solution in case 2 is sometimes referred to as the repeated roots form.
If the discriminant is negative, this corresponds to case 3. The general solution for case 3 can be written using cos, sine, and/or the exponential function. This is sometimes referred to as the trigonometric form. It turns out that case 3 and case 1 are related, and we will see how in a later module.
We will study and solve a series of example differential equations, which corresponds to these 3 different cases, starting with case 1 in this module. Slide 8. Example of 2 real different roots. Consider the following second-order differential equation. Here we have deliberately chosen a differential equation that satisfies the condition of case 1. We will solve the question in 2 stages.
In the first stage, we will find the general solution to the differential equation. That is, we will find the most general function p, which is a function of t, such that the second derivative of p minus 5 times the first derivative of p plus 6 times p is equal to 0 for all t. We do this in steps 1 to 5.
Then in the second stage, we will evaluate the arbitrary constants in the general solution to find the particular solution. To do this, we will need 2 conditions on p and t. To help with your understanding, our examples will be presented in a double column format, where the left-hand column corresponds to the basic theory and the right-hand column corresponds to the theory applied to our example. Step 1. Our first step is to rearrange the differential equation into a standard form. Here, this means we must rearrange the differential equation so that all the terms containing p are on the left-hand side, so that here the right-hand side is 0. We also write the left-hand side in the order of second derivative, then the first derivative, then p. We will see that this ordering is important in the next step.
For our example, we note that our differential equation is already in standard form, where all the terms containing p are on the left-hand side and they appear in the order second derivative, first derivative, and then the function p.
Even though this example is already in a standard form, it is important to put the dE in standard form for the methods here to work. Step 2. We then write down a very special quadratic equation called the characteristic equation, sometimes also called the auxiliary equation. To produce the characteristic equation, we replace the second derivative, d2p dt squared, with k squared, the first derivative dp dt with k, and p with just 1. Please note that it doesn't matter which symbol we use in the characteristic equation. Here we have just chosen k, but some courses use the Greek letter lambda, or m for instance.
For our example, the characteristic equation is then k squared minus 5k plus 6 is equal to 0.
At this stage, it is not obvious why we are using the characteristic equation, but we will use the solutions to the characteristic equation to construct the general solution for the differential equation for each of our cases. We will deal with this in more detail in a later module. Step 3. Here we solve the characteristic equation.
That is, we want to find the values of k such that k squared minus 5k plus 6 is equal to 0.
There are many ways to find these values of k. One way is to use the quadratic formula. The quadratic formula says that k is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a.
For our example, k is equal to minus negative 5 plus or minus the square root of negative 5 all squared minus 4 times 1 times 6 all divided by 2 times 1.
The expression under the square root sign, which is b squared minus 4ac, is called the discriminant. We note here that if the discriminant is positive, then there will be two real and different roots of the characteristic equation, which we will call k1 and k2.
For our example, the discriminant is negative 5 all squared minus 4 times 1 times 6, which is 25 minus 24, which is positive 1. Again, we note that because the discriminant is positive, then there are two real different values for k. Thus, the solutions for k are 5 plus or minus the square root of 1 all over 2. The two solutions are then 5 plus 1, which is 6, divided by 2 gives 3, and 5 minus 1, which is 4, divided by 2 gives 2. Here we choose k1 to be 2 and k2 to be 3. We note that in this example it is much easier to solve the characteristic equation by factorizing it by hand. But here we use the quadratic formula because it is the easiest method to use for more complicated examples.
In practice, you should first try to solve quadratic equations using factorization by hand whenever possible, as it can be much quicker and simpler. Step 4. In step 4, we decide which case to use. As we have already seen, if the discriminant is positive, we get two real and different roots. This corresponds to case 1 in our flowchart.
Because we obtain two real and different roots, k1 equals 2 and k2 equals 3, our example therefore corresponds to case 1.
Step 5. In step 5, we use the roots to the characteristic equation to write down the general solution. If there are two real and different roots to the characteristic equation, which again corresponds to case 1, then the general solution is the sum of two exponential functions. Here, the general solution is p of t is equal to ae to the k1 times t plus be to the k2 times t, where k1 and k2 are the two roots that we have already found, and a and b are arbitrary constants.
For our example, the two real and different roots to the characteristic equation are 2 and 3. Here we have chosen k1 to be 2 and k2 to be 3. We note here that this choice is arbitrary. Therefore, the general solution is p of t is equal to ae to the 2 times t plus be to the 3 times t, where a and b are arbitrary constants.
Now we note that we could have swapped the names of the arbitrary constants. This would give us be to the 2t plus ae to the 3t. This second form is still a general solution of the differential equation, albeit in a different form. You can choose which form to use. If you continue on to find the particular solution, then whatever form you use for the general solution, the particular solution will turn out to be the same. We will see this later. We also note that we could have used different names for the constants. For example, some texts will use A1 and A2 instead of A and B. Ultimately, one can write the general solution in many different forms, but if we are consistent with what constant goes with which exponential, then the particular solution will turn out to be the same in the end anyway. At this stage, we have found the general solution to the differential equation. The general solution represents the set of all the functions p of t that satisfies the differential equation. Now we will continue on to find a particular solution, which not only solves the differential equation, but also satisfies the given conditions on p and t. Step 6. To find a particular solution, we use the conditions on p and t to evaluate the arbitrary constants. We firstly need to understand exactly what our conditions mean for the variables p and t.
The first condition is p of 0 is equal to 1. This means that when t is equal to 0, p is equal to 1. The second condition is p dashed of 0 is equal to 5. This means that when t is equal to 0, the derivative dp dt is equal to 5.
Because the second condition tells us the derivative of p at t equals 0, we need to differentiate p to use this condition.
Using the chain rule on each of the exponentials in the general solution gives us dp dt is equal to 2a e to the 2t plus 3b e to the 3t.
We now substitute these conditions into the general solution and its derivative to obtain equations for a and b.
Because the first condition says that when t equals 0, p is equal to 1, we use the general solution and substitute 0 for t wherever t occurs, and similarly substitute 1 for p wherever p occurs. This gives us 1 is equal to ae to the 2 times 0 plus be to the 3 times 0, which simplifies to the equation 1 is equal to a plus b. Unfortunately, this single equation doesn't have enough information for us to find both a and b independently. We also need to use the second condition. Now recall that the second condition says that when t equals 0, the derivative dp dt is equal to 5. So using the derivative of the general solution, we substitute 0 for t wherever it occurs, and substitute 5 for dp dt wherever it occurs. This gives us 5 is equal to 2a e to the 2 times 0 plus 3b e to the 3 times 0, which simplifies to 5 is equal to 2a plus 3b. For this example, we get two equations, and both of these contain the two unknowns a and b. We need to find a and b that satisfy both of these equations.
Here, neither equation alone allows us to find a or b, but we can find a and b by solving the equations simultaneously. These simultaneous equations can be solved using either substitution or elimination. Here, we will use the elimination method.
Labelling our equations 1 and 2, we multiply equation 1 by negative 2. We call this new equation equation 3. The reason for doing this will be apparent in the next step. We now simply add equation 2 to the new equation 3. To do this, we just add the terms down the columns. Minus 2a plus 2a is equal to 0. Minus 2b plus 3b is equal to b. And minus 2 plus 5 is equal to 3. This produces a new equation 0 plus b is equal to 3, where a has been completely eliminated. The reason that a does not appear is that we have specifically chosen to multiply equation 1 by negative 2, so that when we add this new equation to equation 2, all the a's cancel out. This same method of elimination can be used to solve any such linear equations. Hence, b is equal to 3. We now substitute b is equal to 3 into either of the original equations to get a. Substituting b equals 3 into equation 1, which is simpler, we get a plus 3 is equal to 1. Therefore, a is equal to negative 2. Thus we have found that a is equal to negative 2 and b is equal to 3.
Having found values for the constants a and b, we can now write down our particular solution.
Here, substituting a is equal to negative 2 and b is equal to 3 into our general solution, we get p of t is equal to negative 2 e to the 2t plus 3 e to the 3t. It's important to understand what our particular solution actually means. It is a solution to the differential equation, and, just as importantly, the particular solution satisfies both initial conditions. That is, the solution goes through the point 0, 1 and has a slope of 5 at that point.
Slide 13. Summary of steps for our case 1 example.
In this module, we have derived the solution slowly and carefully to help you with understanding, but the steps in the process can be easily summarized.
In step 1, we rearranged the differential equation into a standard form, and for our example, the equation was already in this form.
In step 2, we replaced d2p dt squared with k squared, dp dt with k, and p with 1 to produce the characteristic equation.
In step 3, we factorized the characteristic equation and got k1 equals 2 and k2 equals 3.
In step 4, we used the fact that the roots were real and different to use the form of the solution in case 1.
In step 5, we use the roots to write down the general solution. We then continued to find the particular solution.
In step 6, we use p of 0 is equal to 1 to substitute t equals 0 and p equals 1 into the general solution. And we use p dashed of 0 equals 5 to substitute t equals 0 and dp dt equals 5 into the derivative of the general solution. We then solved the resulting equations simultaneously and found that a is equal to minus 2 and b is equal to 3.
Finally, in step 7, we substituted a equals negative 2 and b equals 3 into the general solution to find the particular solution. Slide 14. Verifying our example using substitution.
This completes the solution to the problem, and if you're asked to solve this problem, you can just stop here. To reinforce our understanding of what a solution means, we now verify that our p of t satisfies our differential equation.
To do this, we need to find the first and second derivatives. We then substitute the solution and these derivatives into the differential equation. The left-hand side of the dE is then the following. When we substitute for p and its derivatives, we then get the following. We then expand the brackets. Now, all the e to the 2t's cancel, as do all of the e to the 3t's, giving us 0, which is equal to the right-hand side of the dE.
This verifies that the function is indeed a solution to the dE. This does not happen for any arbitrary function. Again, not only does the function satisfy the dE, but it passes through the point t equals 0, p equals 1, and at t equals 0, the slope of the curve is equal to 5. When you think about this, this is no arbitrary function and not something that could be easily guessed.
This completes the first module in this series.
Here we explain the meaning of each of the terms second order, linear, homogeneous, and constant coefficient.
We then explain how the 3 different cases result from the characteristic equation.
And we demonstrated how to solve our differential equation when the characteristic equation has real and different roots.
In the later parts of this series of modules, we will explain how to solve the other cases for this differential equation.